Hello again. So today we're going to be talking about the squeeze theorem and show some applications of the squeeze theorem and how it might be presented in a problem on your homework or on test. Okay, so here is the squeeze theorem. If we have three functions, f, g, and h, with f being less than or equal to g, which is less than or equal to h, for all x in an interval around x equals a, but not necessarily including a, and the limit as x approaches a of f of x is L, the limit as x approaches a of h of x is also L, then g, which is the middle function, its limit as x approaches a also has to be L. Okay, so this problem is a whole, or this theorem is a whole lot. It's best to look at an example to understand exactly what's going on with this theorem. Okay, so let me draw a graph and explain on the graph. All right, so here we have a graph of the situation. We have three functions. One, f of x, as you see, is always below the other two. The other one, g of x, is above that, although it touches it there, and h is bigger than all three of them. Okay, now this relation only has to hold for a small interval around a. I made it true for all real numbers. That's okay. So f and g and h have that property that f of x is less than or equal to g of x, which is less than or equal to h of x. Also, I made this problem where the limit as x approaches a for f goes to a height of L. This is our function f. And then h is also going to L. And then look what happens to g. G gets sandwiched in between these two, because as x approaches a, both the blue lines, which are sort of boundaries for g, both go to L, so g, being sandwiched between those two boundaries, also has to go to L on both sides. Okay? And you can make this problem where maybe even all three of the graphs might even have a hole at x equals a, and that's okay. Because remember, in the statement of the theorem, the f and g and h have to have this relationship in a neighborhood around a, but not including a. So a is not necessary. Also, remember that for limits, the value of the limit is independent of the value at that point. So at x equals a, anything can be going on. All 3 points can be missing. We could have like one of the points existing and the other two don't. That it doesn't matter what's happening at a, only in a small neighborhood around a. Anyway, so this is the squeeze theorem, and this is how it's applied. What the heck is it useful for? Okay, so I'm going to give the most classic example of a problem in which the squeeze theorem can be applied, and then we'll look at a couple more examples of some similar problems that are related to that first problem and show how the squeeze theorem can be applied to those problems as well. Okay, so this graph is the secret behind creating the three functions that we need. So what I've done here is I've created part of a circle of radius 1 and then made a couple of other triangles that are around it. Okay, now obviously the area of this little teeny triangle is smaller than the area of the wedge, which is smaller than the area of the biggest triangle. So let's set up an inequality that expresses this. The area of the smallest triangle, using just the area of a triangle, 1/2 base times height, would be 1/2 cosine times sine. So 1/2 cosine theta times sine theta is less than or equal to the area of the wedge. Okay, now how do you get the area of a wedge? The way I like to think about it is to break it down into sort of two parts. First, what is the area of a circle? And that's pi r squared. And the radius of our circle is 1. So the area pi r squared would just be pi. Okay, that's the area if we had a full circle. But we don't. We only have a fraction of it. What fraction? Well, theta, if we express it in radians, a full circle is 2 pi radians. and our angle is only an angle of theta radians. In other words, our wedge is theta over 2 pi. That's the percentage or fraction of the entire area of a circle. So it's theta times, and then the fraction of a circle that our wedge is theta over 2 pi. Okay, finally, the area of the biggest triangle is 1/2 base times height, so 1/2 of 1 times tangent, which is just tangent of theta, which tangent can also be written as sine over cosine. And you'll see in a second why I did that. Okay, so the middle expression, we can just simplify that by canceling the pi's into theta over 2. Next step, multiply by 2 everywhere to get rid of all these 1/2. So that 1/2 disappears, that 1/2 disappears. And then this middle is now just theta. Finally, our last step is going to be to divide by sine on all 3 sides. Assume that we're in the first quadrant so that sine is positive, so that the direction of the inequality doesn't switch. So now we have this relationship, okay? Now we have 3 functions. We have something that is like the limit I wanted to evaluate, it's just upside down. So we can just fix this by inverting both of these, and like when you have 4 is less than 7 and you flip it, 1/7 is now less than 1/4, and so the direction of the inequality is going to get reversed, which means, okay, flip the middle, flip that getting cosine, but the inequality direction would then be reversed. So this is greater than or equal to cosine. So this just got moved over there. And then 1 over cosine, and switching the direction of the inequality is just going to move it over here. Okay. Now, let's think about the limit as x approaches 0 of cosine of theta. Well, cosine of 0 is 1. So, let's see. Yeah, let me erase the diagram and use the area of the chalkboard up here. So the limit as theta approaches 0 of cosine of theta is 1. And if we look at the limit as cosine or theta goes to 0, 1 over cosine, we get 1 over 1, which is also 1. So we've now activated everything that we need to apply the squeeze theorem. This is our f of x, g of x, h of x. The value of a is 0, and we've shown that the limit as theta approaches a for both f and h are both 1. Therefore, the limit of the middle equation is also 1 by the squeeze theorem. So the limit as theta approaches 0 of sine of theta over theta is 1. Okay, so now that was a little bit complicated because we had to draw a diagram, explain, the areas. You probably never would have thought of to do that on your own, and thankfully you really don't have to. I mainly showed you that because sometimes on the homeworks they try to use a diagram like that and get you to use it to solve a problem, but it is really hard to put into a homework problem. But it is nice to see it at least once. As you'll see, now that we know this limit, we can actually use it to get some other limits. Okay, so let's do a couple of other problems that will actually use this limit and skip having to even do the squeeze theorem, although this limit actually comes from the squeeze theorem. So let's do a couple of examples like that. Okay, so Here is a problem, limit as x approaches 0 of 1 minus cosine x over x. And if you try to just plug in 0, you wind up with 1 minus 1, the top's going to 0 and the bottom's going to 0, so 0 over 0. And because it has trig functions, we know we can't use any of the techniques from the last video. Although, because we have trig functions, remember that you might be able to use trigonometric identities to solve some problems. And that's the key to this one. What we're going to do is we're going to multiply by 1 plus cosine of x on the top and bottom. The reason for doing this is because 1 minus cosine times 1 plus cosine gives you 1 minus cosine squared. And whenever you have trig functions that are squared, you should be thinking about the Pythagorean theorem or Pythagorean identity. Because by the Pythagorean identity, sine squared plus cosine squared equals 1. Therefore, if you subtract cosine squared on both sides, you see that sine squared of x is 1 minus cosine squared of x. So we can just replace the numerator with sine squared x. Now, what good does that do us? Well, notice we now have sines of x on top, and we have a x on bottom. And that limit that we just solved a second ago was the limit of sine of x over x. We have a sine of x over x now. So let's factor that out of the rest of the fraction. Now let's look at it. We know that sine of x over x goes to 1 by that special limit from before. Now let's think about this other one. If we try plugging in 0, the top would be going to 0. The bottom would be going to 1 plus 1, which is 2. So 0 over 2 is just 0. 1 times 0. So the answer is 0. 1 times 0. So the entire limit is 0. So you see how this problem used that special limit as x approaches 0, sine of x over x, in order to solve the problem. So technically speaking, the squeeze theorem I didn't use in the problem, but this is from the squeeze theorem. Okay, let's look at one last example. All right, so here's another example of a problem that we're going to use the squeeze theorem on. Except we have one little annoyance that this is not sine of x, it's sine of x to the 4th. So what are we going to do about that? And you'll see why I did 0 from the right a little bit later. Okay, so whenever you have a problem where you don't have just x inside of your trig function, instead you have another expression, what I like to do is I just try to copy that expression into the denominator. Okay, so how can we make an x to the 4th be in this denominator? Well, we'd have to multiply by an extra x cubed. So let's multiply by x cubed on the top and the bottom. So now we'd have this. Okay. As x approaches 0, x to the 4th approaches 0. So you can sort of think of this part of the expression that as x approaches 0, because both of these are approaching 0, then you have like sine of y over y, where y approaches 0. So this is going to go to 1. And the rest of it is just x cubed, and approaching 0 means it goes to 0. So your answer is 0. So it turned out that that plus I really didn't need it. I could have just done a regular limit and it still would have been 0. Okay, so I think that's good enough for the squeeze theorem. The squeeze theorem is a problem that is a little bit tricky for them to put into homework problems and the tests, but usually at UT they're pretty ingenious on how they design the problems, and usually there will be several problems that either use a squeeze theorem or at the very least use that special limit as x approaches 0 of sine of x over x equaling 1. So that's an important limit to have memorized, and it'll be used most often, well, it'll be used in problems that involve trig functions. Okay, I think that's good for now. See you in the next video. Have a good day.